I will get the hang of this, I promise. Someday. All right, onward. Let's do this. Domain and range, we've mentioned this before. This isn't like new territory, as far as I know. The domain piece, the only thing about it is there's means of writing like the restrictions on domain. You guys know I'm in note packet, right? You're all good? Does anyone need an extra note packet? Okay, so those are loaded somewhere. I can get those out to you. The big deal, all right, the function has a set D, let's see, from a set D to a set R is a rule. Now a rule, it's a funny thing is, we actually teach this in elementary school way better than we used to, so I'm sorry you're not getting the same education as your maybe younger siblings. But R is a rule. They talk about rules all the time, and really that's actually a function or equation. Isn't that cool? But these kids are able to figure out, like, if I add 2 to this number and subtract 4, I will get a certain result. And that all they know is it's a rule for getting from one number to another. We know it as a function. How do you get from one value to another? What's the process that gets you there? So it's a rule that assigns every element D to a unique element in R. Domain and range are the D and R that you're seeing there, capital R. So D is the input of called domain. So I'm going to fill those in. Nothing crazy about that. But we do use D and R, and then there's some other places where D and R get confused, so we have to be distinct at that point. And R, of course, stands for range. And that's the story about those guys. So nothing fancy. But function notation, which you've had before, as far as you're doing your interval function notation for functions, we're going to use the brackets brace system or the parentheses system. There are plenty of times where other systems work just fine. It's just it goes along with your textbook, and we're just going to be consistent. I like it. It's clean. It's efficient. So all those things are good. The function notation that we use is y equals f of x. This means it's kind of redundant in some ways. So if I say y equals f of x, I am saying y, my output, is some function of x. It's just defining more than anything. It's defining it as another letter f. It's also saying that x is your input. So if I said y equals g of a, that's just saying, oh, y is also known as this function g, which is really weird. And a would be my input. So the parts that are important are knowing that that letter inside represents your input that goes in. And the letters here become interchangeable. The y and the f. If I did y equals g of a, then g and f, or y and g would be interchangeable. So the read as, we read it as y is equal to f of x. So I'm going to write really small in here. I don't know if you guys can squeeze it in there, because I got this super expandy screen, so that's an advantage for me. But y and then equals, I'm not going to write that out. You already know that word, f of x. So that's the word or verbiage. The other one is, so you're good with that, f of x, the value of f at x. And that comes up every now and then. The value of f at x is another way to look at it. So it's the function value. And that's a vertical value. So f, or the function output, is vertical. X, your input, is horizontal. Good things to know. So the idea is here, in this case, x is your domain, and y, your output, is your range. So x values, or possible x values, is your domain. So I'm going to write x values possible is really your domain. I'm going to put a little arrow here. Okay, let me know if something weird shows up on the screen. Sometimes I miss it. And y is the y values, or the possible values of y, the range. I'm writing down here because I want more space. Ooh, 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 ooh. So that's it. That's the process. Those all, I hope, redundant, something you've seen before. Here you can see the whole thing, I hope. It's not too small on your screen. But that's it. That's your big piece. Other graphs down below. So we should jump to things we've totally probably bored you with in the past, but they're really important. this, in this graphing, I want to add some things to this graph. There's some errors that probably should be fixed. There should be some like endpoints that stop these graphs here. The way we have it marked in here is as if it stops on the ends of these particular windows. Okay, so I'm going to put endpoints there. You actually don't know a graph stops unless somebody says it does, or there's some marking like that dot that says over. Done. This thing ends there. Because the way these are marked right now, the negative 4.7 to 4.7 and the negative 3.3 to 3.3, we're looking at our domain and range for each one of these. Okay, so there's your domain listed in there, and then this one's the range in that window. So they're written for you. And it's just looking at the window carefully. So which one seems to go negative 4.7 to negative 3.3 to 3.3. Interestingly enough, you notice these are the same domain and range for each of these, but we're looking at very different functions. So the idea is that domain and range is all possible values of x and y respectively. And you know the word respectively means, so if I say domain and range, and then afterward I say values of x, comma values of y, and I say the word respectively, I mean it's how I said it the first time. I mean also how I said it the second time. They follow the same order. You probably all know that, but the next one is same kind of, a different kind of graph, but it has the same domain and range. They look totally different, but domain and range is just describing the possible values of x and y. It doesn't matter what the graph looks like. It doesn't describe its shape, but it sure gives you a sense of where it starts and ends. So another domain and range at the end. But not all of them are functions. So of the three graphs shown below, which one is not a graph of a function? Anyone want the Cupid doll on this one? You name it. Is it A, B, or C? I heard it. You got it. C. I also heard that like slithering. You're right. So if I draw a vertical line through there, it hits 3 times. If it hits more than once, anywhere you draw it, you got a non-function. The others are good. So yeah, this is definitely our vertical line test failure at the last one. So if I make this big, vert line test failure. That's the French spelling of failure. Okay, just go with it. I don't know what it, man, that's rotten. Okay, that's the piece. What do you think? All good so far? Stop me if you need something. Y equals x squared represent y as a function of x. After all that, if I said, does that represent y as a function of x? If I say y equals x squared, does it seem like some of you say yes, some no? This is where notation can blow your mind for a while. Does it represent this? It does. Okay, so y equals x squared represents y as a function of x. And the answer is yes. Okay, all that means, so let me interpret that. I love that that's in here in the notes because after all that, you might not know. But what, yeah, this is definitely a definition. To say that y is a function of x, it just means you're graphing y and x is your inputs. Okay, so y is a function of x. This translates to y is the output. Back up. Y is your output. And x is your input. Okay. That's what it means. And so if that's true, we do have that y equals x squared. Y, the value of like the height of that parabola, because we know what it is. And then x is the input value. So if I said x is a function of z. Ooh. So I'll put off to the side here. Let's get really wild. If I say x is a function of z, this is another way of writing x is a func of z, is also known as, ready for this one? Ready for this? I could write anything. Could be z to the third. These are all examples that would work. It could be z plus 2. It could be x equals 1/3 z to the 1/2 all over z minus 5. My favorite function. If I say x is a function of z, all it means is x is my output, and then z would be my input. So as wonky as that all sounds. And it doesn't specifically say what type of function it is. And there's other ways to write it. There's function notation. But that verbiage is important. Okay. Cool. You want to throw an example at me? You guys think that's weird? Got the vertical line test. I think you only have, there's some verbiage to it. I'm going to write it really fast. Basically, vert line cannot touch more than once on the function of the graph. So cannot, let's just get that done with. Touch greater than one time. Ooh, that's throwing some mathematical lingo, some symbolic stuff. Okay. This next piece, this is where the crunching kicks in. We've done a little bit of it. So if we're going to do, if the function has a fraction, set the denominator equal to 0 in order to exclude values of x. So these are ways, these are just kind of tricks of the trade. So domain is possible x's, and actually we deal with finding possible x's by the most efficient way is you find not possible x's, x that are not possible. So I'm going to write non-possible. It's really bad grammar probably. X values. You can write it better. To exclude. That's what we're going to work from. Because we're going to basically say, yeah, it can be any x except that one. You guys know the Henry Ford story. Somebody came in and asked, I would really like a Model T. And he says, Henry Ford said to whoever came in there, said, you can have it any color you want, as long as it's black. So basically it was kind of excluding. It's a way of, that's kind of an interesting domain, or that's actually, is that a range question? I guess that's an input value. You choose your car, and one of the inputs is color. But he wouldn't let you choose any other color but black. And I don't know how that conversation actually went, but it's a fabled conversation. Any color you want but black, as long as it's black. Okay, screen, fit. If the function has a fraction, set the denominator equal to 0 in order to exclude values of x. So that's huge. So I'm going to give you a real simple example, and I'm going to squeeze it in there, and I don't know if you guys can make this work. All right, let's use function notation like f of x. Okay, and let's do 1 over x plus 1. And is there any value of x that isn't going to work? -1. So that's actually where we're going to start. The domain is all reals except 1. So domain is, I'm going to say, well, that's kind of a fun way to look at it. I'm going to say everything, all reals, except x equals -1. And the way we find that, in case you're wondering, the more complicated it gets, the rule up above says the way you found that -1, you probably did it all mentally, which is great. You should be able to do that. See? Someday they're going to figure this out. Why we always get this like error update. It's trying to back up to some system and then all day long. Okay. But what we have to do is take that x plus 1 in the denominator, set it equal to 0. That's what the instructions are saying. Solve for x. And that value, by setting it equal to 0, we're saying, let's find out when it wouldn't work. We can never, ever divide by 0. So we're setting it equal to 0 to find out one of the domain limitations. And that's what we're working from. Okay. That's where that came from. The other, all right, is this. If a function has a root, this is part 2, with an even index, so set the expression under it greater than or equal to 0 to find the domain. You're probably wondering what on earth this even index. So let me give you an example-ish kind of thing, and then I'll explain some of the terms. Let's use this one. Okay, so a root with an even index.